No, it's on. Um, so this is an unusual seminar for the Leon Group. We're usually over in another building, and so this is new territory. Thank you all for coming on Friday today, in the morning early. It's really a great pleasure for me to introduce to you someone that I've known for many years in Hawaii. He was an undergraduate and involved in learning astronomy. He's been an astronomy graduate student and an information technology graduate student, and he's been part of I think at least two startup companies that I know about, or is there more? Maybe more. He's quite a creative young man who has been in Hawaii now for, I don't know, 15 years, which is longer than most graduate students, but he made it out, and he's now come to help us in the Leon project in a very important area, which is to use machine learning to be able to measure wavefronts and make this telescope system that we're building work. It's a crucial part of the system, and I'm very happy to introduce Ian, who's going to talk about problems related to measuring wavefronts very accurately and using them to control telescopes to do things that right now no other telescope can do. So greetings, Ian, and thank you for coming.
You guys hear me? Good. Aloha mai kako. My name is Ian Cunningham. All right. Yep. Aloha mai kako. My name is Ian Cunningham. Yeah, I've been in Hawaii for 15 years. I've known Jeff for 11. I have not been in grad school for 15 years, though. But I went to the University of Hawaii Hilo as an undergraduate, worked with Jeff for quite a while, and then he conned me into going to grad school for a bit. But yeah, I made it out. And most of the time I was in grad school, I was working on various parts of this wavefront sensing problem, using the focal plane and using deep learning. So I'm going to go over a lot of different things, and I didn't quite know like what level to pitch things at, and I wanted to explain concepts. So it's going to be gliding over a lot of stuff. And if I'm a little hallucinatory, it's because my schedule doesn't align properly, and so I just didn't sleep last night. But yeah, please stop me if you have questions or if you have objections about something I said. I probably just glossed over something, but basically what I want to talk about today is a little bit the background of what focal plane wavefront sensing is, specifically how it's going to be applied for ELF. That's the majority of my talk. But I did spend the last year of my grad program working with Dr. Mike Bottom on how to use the same technique or an extension of this technique for chronographs. And that's also an area where this is doing something that's never been done before. And then finally, I've extended this a little further besides deep supervised learning, which most of this is, into deep reinforcement learning. So I'll talk a little bit about that and future things that I want to talk about, or future things I want to work on. So yeah, what is focal plane wavefront sensing? So basically, hopefully you guys know, or you've seen some version of this diagram before, but you have some kind of atmosphere that you're seeing through when you look through a telescope. And it's sort of like if you had a heat haze, you know, if you look down a highway and you have a heat haze, it's the same kind of problem. It actually delays the light to the mirror at different places in the mirror, causing distortions in the optical surface, or things that appear as distortions in the optical surface, which deform the image. So the light goes through all of this, is focused in the telescope, comes down, at some point it hits a beam combiner and the data goes to an imaging sensor. But before that, it gets split off to like a dedicated wavefront sensor in most modern observatories. So that's like a Shack-Hartman or a pyramid wavefront sensor. They're very expensive, very advanced pieces of technology. They're amazing. They enable a lot of modern astronomy to outcompete space telescopes in a lot of cases for getting near similar or beyond that diffraction limit. But we want to get rid of the wavefront sensor entirely. So we just want to not have that at all. And what we're going to do instead is directly sense the wavefront. So that's this deformation in the wavefront, just by what the scientific camera sees. So what does that look like? I'm going to be doing a lot of these kind of plots. So I just want to take a second to explain. If you have kind of an ideal system, ideal optical system, the electric field right before you go into focus, you can represent as this pupil plane. And so this represents the phase of the electric field right before it hits the focus. It only goes from minus pi to pi because it's in radians. So if there's a path length difference that's one wavelength of light, that will look identical in the monochromatic case of a single wavelength of light. So that's going to be important at some point later. So I figured I'd mention it. Anyways, path length differences show up here on the left, and then you get out this point spread function, which has this bright core, and this is many orders of magnitude. So in practice, if you looked at this on a linear scale, it would mostly just be this very bright center point here, but we're looking at 5 orders of magnitude here. So you can see down into the structure of the point spread function, as we call it. So we start adding some actuations to this mirror, and you can see the effect. The first is tip and tilt, and that's pretty intuitive. So it's just if you have a mirror and you're to slightly move it up and down, just tilt it. That's what those modes are. So those are the mode 1 and 2 of the Zernick keys. This is defocus. And for each of these, you can see there's a pattern on the left in the wavefront sensor, or in the pupil plane. And then there's a pattern in the focal plane. And we'd hope that you could just directly one-to-one take this fairly unique looking pattern on the right and predict the errors on the left. It's not, unfortunately, quite that simple, but that's the gist. So this is just the first 9 Zernick keys, but we can skip past it. They do look pretty cool, though. So I'm going to skip right ahead to what we want for segmented mirrors, which is we're just going to take those first 2 modes that we just looked at to start with, just the tip and the tilt, and we're just going to apply it to 1 telescope. So this is a weird ELF. It's not an ELF you would build, hopefully, but it's still a ring of aperture of mirrors, and it's symmetric, which is actually not good, but that's why I made it this way. And it has a pretty interesting PSF. So I don't think you would want that PSF, but anyways, illustratively, it's interesting. So if you tip one of the mirrors, you can see that the area pattern of a single aperture actually slips out from all of the rest. And at some point, it's like identifiable as a normal area pattern. But in the meantime, there's all these interesting interference patterns that happen around the edges. And so that kind of interference pattern in the fringes is what allows us to individually identify which mirror is doing the tip and the tilting. So we can do the same thing, but with just pistons. So piston's one we hadn't done yet. Piston is literally just in the ideal pupil plane if you push the mirror forward and back. If you just add a uniform phase to the whole mirror. So if you just do that to a single mirror, you get this pretty interesting screen door effect that's happening. So as you vary this one, again, it's actually going through a whole wavelength of phase, but because it wraps around, it's not intuitive what's happening on the left, but it's going up 1 phase and then coming back down 1 wavelength of light. And you'll start to see that if you look carefully at this, which might not be possible on Zoom, so I apologize for that. But this looks unique. As you cycle through the piston on this aperture, it looks unique. And then this other one looks unique because it's in a different direction. But when you get back around to this one, it's unfortunately the exact same pattern again. And that symmetry is a problem. So that is why ELF is not symmetrical. Breaking this kind of degeneracy. So the degeneracy comes from the fact that you have a phase between each of the mirrors, and you can think of it as a baseline. So there's every point on this mirror is interfering with every point on this other mirror. But there's this sort of constant vector that points in this direction and with this length, this distance between them. But if you flip it around and you're trying to figure out what's happening with this mirror, unfortunately, this vector is the same as this vector because it doesn't care about where the position is. It just cares about the direction and the length. So once you make it asymmetrical, there's no redundant baselines. So we're good. And this technique is used all the time. So this is actually the JWST. It's a way of phasing the JWST by putting asymmetric masks in the pupil so that they can identify the individual phases of those segments that they've masked off. So each of those arrangements makes unique patterns that allows them to drill down into the overall errors of the segments and dial them in very accurately. Keck does similar, or it used to. So yeah, this is the mini ELF, or self, sorry, it's long ago, self aperture. So it's 15 rings and has a much prettier PSF until you add some piston tip and tilt. So this is what we're trying to retrieve. It kind of looks like a mess. How do you go from this to, so it's 15 mirrors and it's piston tip and tilt for each, so it's 35 values. And that's what we're trying to solve here. And just to backtrack a little bit, Jeff first kind of started me on this problem almost 10 years ago, I think, with Colossus, which was the precursor to ELF, which was a much more filled aperture. And he developed a technique for doing this, the co-phasing, but with just the piston. And it exploited all of those baselines in the image. I'm not going to go into the details, but he gave it to me. I knew nothing about optics, but I treated it as a black box computer optimization problem, and I made it basically work. Not very well, but it did work actually. But having it in front of me that for so long, in that time afterwards, I kind of self-taught myself a lot of machine learning, eventually got into deep learning, actually went and worked for a startup doing machine learning. And so by the time I got to grad school, I actually had some experience training deep neural networks, and it came in front of me again. And it seemed like a really clear application. The way these image models work, I mean, especially 10 years ago, the big kahuna in terms of models at the time was still ImageNet. ImageNet, you know, takes a random picture and tells you if it's a dog, and tells you the specific species, and it tells you the, you know, et cetera, et cetera. So it's a pretty basic problem in deep learning at this point. But basically, you're taking in an array of pixels and you're regressing that to some kind of output. In this case, it's categorical, but you can regress it to pretty much anything that you can put a label. So that's essentially what we did. So yeah, basically just formulating it as a supervised regression problem where you have inputs, which are images, and the output is the piston tip and tilt. It's really all there is to it. There's a lot more that goes on to how you implement it well, or implement it so it learns quickly, or continues learning after a lot of examples have been given to it. But the basic formulation is that easy. Image go in, regression to the values you're feeding it. And so you just generate a ton of simulated data, throw a bunch of GPUs at it, and out pops a model, right? Basically. So this is a basic schematic of the neural net architecture. I'm not going to spend a ton of time on this because I'm trying to cover a lot of random things. But I actually did a decent amount of architecture search. If anyone wants to ask me about that or optimization or any deep learning stuff, I'd be happy to ask or answer. But this is a very simple model in terms of the kind of models that are out there. And I've actually tried that state-of-the-art image model or ImageNet model, which is incredibly complex. It's, this is like 6 layers deep. It's like hundreds, thousands of layers deep. It's really overkill, in my opinion. But I actually did try to train it, and I actually saw almost no improvement off this extremely simple architecture. So don't be fooled by the simpleness. It works really well. Yeah. So we started off in the beginning with the very basic problem. This is before so all these plots and everything and all the training that I've done for the chronograph stuff and this and everything is all using a little software package I wrote in Python called Telescope Sim that's meant for this, where you can just give it a configuration of the telescope, and you give it a configuration of the filter bandwidth and the filter center, the aperture details, and then it formulates it as give it an input, get an output, and perfect for generating data sets. So anyways, in the beginning, we were essentially doing exactly what I said before. You're just imposing random piston tip tilts. You get some kind of point spread function. There's no noise floor. So this is extremely optimistic, but we just wanted to make sure it worked. And there's no atmosphere. There's no extra noise in the wavefront domain or in the detector domain. And it actually took a little bit to figure out how to get it to running, and we tried a bunch of things. One of the first things, kind of breakthroughs that we had that really worked well, was actually using 2 filters. So if you had like something to split the light into, say 500 nanometers and micron, looking at those 2 filters at the same time, feeding that to the model, was one of the first things that made it work really well. But I was still doing everything monochromatically at that time. So I was only simulating a single ideal wavelength for each filter. What I found when I developed this out better and started adding some filter bandwidth is that was actually enough, surprisingly. A single filter. So if you have a filter at 1 micron with like 0.2 fractional bandwidth, and you simulate that by sweeping the simulation through, say, 10 or 13, some number like that, wavelengths in between every time you generate a sample. You generate 13 different wavelengths, and that approaches the reality of bandwidth in the optical simulation. That was enough. Just giving it that bandwidth was surprisingly enough to let it train really well. And it actually, this is kind of important, but kind of niche, is that it works outside this phase wrap regime, and that's actually really important for ELF. So as I mentioned earlier, in the electric field, if you move the wavefront by a single wavelength of light, then that's indistinguishable from 2 pi radians later or 4 pi radians later. So this was actually retrieving things that were like, I can't remember the number, but like 10 wavelengths or more, and with like no ambiguity. So that was really promising, because ELF might potentially have extra errors that are out of the distribution you might expect. So that worked really well. But then what we really wanted to do was to simulate having an atmosphere. So this is a Kolmogorov atmosphere that HCI Pi will generate for you. And it's got a coherence length of 15 centimeters. And so you see it, I think this is the first time I've actually introduced Strel. So Strel is the center brightness I actually do have it back here, don't I? Yeah, so Strel is in the ideal case, how bright is the core of the image versus all of the encircling speckle. You can define it as the enclosed energy, or define it as fitting the Gaussian peak of it. But anyways, so you can see once you add a bunch of random piston tip tilt and the phase gets very muddy, the peak is now down, 40% of the brightness. So it's an important figure. I use it a lot of places. So this 15 centimeter atmosphere, which should be, I believe, fairly similar to what you would achieve here on an average day, or it degrades the Strel, if uncorrected, quite a lot. But if you just if you fit a linear function of each of the mirrors to optimally fit the atmosphere to remove that. So this is the same atmosphere, but we've just removed a piston, tip, and tilt from each of the sub apertures. We're now up to a Strel of 7. So it's a huge improvement from 1.5. And it looks like a good PSF function. So what we want to do is we want to put in this completely messed up image. And again, we're just putting in this, what the detector would see. And we're trying to get out the corrections that lead to this. And then we want to add some detector noise, because we're not going to have infinite amounts of depth and contrast ratio on signal to noise. So this is a reasonable mid-level example of the signal to noise that I train on. So the parameters of, I actually just dusted this off again for the first time in a couple years, and generated a new data set and trained new models in the last couple weeks. And so the latest approach is training on unreasonably bad atmospheres. These are like 4 centimeters. You might not even go outside that day. You might not even, I don't know if the stars would be out. It'd be really bad conditions, I think, to unreasonably good. So what that does is extremely poor atmospheres give the model the ability to, or at least give it some exposure to extremely bad piston tip and tilt, and extremely bad high frequency noise in the wavefront. And then these very optimistic ones help it with easier corrections. And I varied the signal noise from basically the center peak is barely visible up to about 3 orders of magnitude brighter, so that it got used to a range of that, and so that we can test the performance of how deep the model can see, or how little signal noise we can get away with. And the recent trick I did a week or 2 ago is basically simulating like you're in a loop. So you're giving it partial corrections, and that's helped a lot. So generate about 1 terabyte of data, 30 million samples, run a bunch of hyperparameter sweeps on the training runs, and pick a few that look really good and train them for like 3 days. And what I found with the other problems I've done is that all of that hyperparameter tuning and stuff is nice, but once you find a pretty good architecture, it's more important to work on the data set. It's more important to work on how realistic it is and what you can do to improve the distribution of what you're training on. So I think now that we have a model that seems to be working pretty well, basically anytime you create a new data set, largely what you need to do is just run a really long, training run on that data set. So I don't know how well this will go from Zoom, but this is just an example of a recent training run. So I guess I should explain it before I get started running. On the left is a completely uncorrected atmosphere, and it's going to evolve with time. And then below that, I'm actually summing up the PSF as we go. So it should approach something. And on the right is the optimal, how, like, if you take the atmosphere and you apply the best piston tip tilt that you can get, this is the best correction that you can get. And in the middle is what basically how well the deep learning model does. So it's given an image, it makes a prediction. The atmosphere then evolves. So um, the predictions are always behind by one time step. And then it sees what its previous correction does on the current atmosphere, and then it tries to predict the correction for that. So it's just always playing catch up. Um, but and what I've done with this is I've paused the first frame to try to show how quickly the model converges. And actually, this is a easier atmosphere. So within the first frame, it's already converged quite a lot. So that's not useful. But as you can see, so on the bottom here, we have the Strel that would be of a totally uncorrected atmosphere, which is pretty bad. And the green is the best possible correction of the atmosphere. And the red is how well the neural network is doing. So it very quickly in the first couple frames pops up to near the optimal, not totally optimal. But it does a pretty good job of staying there. So it was 20 centimeters before. This is 15 centimeters, and we're going to try 10 centimeters. So this is a pretty difficult atmosphere, I think. So you can see the top line is very reduced. Even with the best percentile you can provide, the best Strel that you're going to get from that correction isn't super great. It's 0.5 or something. But thankfully, the neural network is actually keeping up with that pretty well. You can see it kind of lost the plot here. But overall, the model is doing pretty well. And I don't know if I can zoom in, but these two PSFs that build up from the summation of all of them are pretty close. So that's promising. Yeah, so the limitations, as I said, the delay is a big limitation. So the longer you wait, the more out of date those corrections that you derive, even if you have the optimal corrections for the last frame, if you wait long enough, they're not going to fit the atmosphere that you have now. So the time you need, the speed at which you need to do this is, it has to be really fast. So that's actually, there are other focal plane wavefront sensing techniques that would work that are more analytical. They're more computationally expensive. But like theoretically, if they could freeze the atmosphere for a second or two, they could correct each step, but we need milliseconds. So that's one of the important things about this model, and something that needs to be optimized quite a lot. So it might need some kind of dedicated hardware to run. Need to figure out what the signal noise range that it performs well is. And I actually pretty close to having those plots, but didn't have them ready for this to go on in a paper, hopefully pretty soon. And real optics. Real optics is a thing. So we'll see in the next project that I'm going to go through more quickly so I actually got my next model working on Subaru telescope with real optics, and my advisor essentially thought I was encouraging the whole time, but essentially didn't believe it until it was actually on optics. And as soon as it was actually running on optics, it was the most amazing thing. But up until that point, it's promising. And the work to get it from working in simulation to figuring out all the disagreements and the reasons that the model might be getting confused takes a decent amount of work. So that's always going to be a bit of a barrier. But it's just something you need to throw grad students at, right? So so my next work I did with Dr. Michael Bottom at UH IFA, but at the Hilo branch. And he's really interested in working in high contrast imaging. So he's worked on the star shade problem, and he's worked on a lot of high contrast imaging problems. And similar to the same kind of goals as ELF, you're trying to get to deep contrast next to a really bright star. So you need to control the wavefront very carefully. So done a lot of work with chronographs. This is just a schematic of how a typical chronograph would work. So you have some kind of focus here, and you put something that essentially it's an intermediate focus before the detector. And like the traditional is like a Leo that would just physically block out this light here. But there's more advanced versions that have, like four quadrant phase mask or a vortex, which is what we're focusing on. And then it goes back, that stray light gets taken out. And then now you have, if you compare this PSF to this, you've gotten rid of most of the central brightness. And that's really helpful when you're trying to see things that are faint nearby. So a problem that these have is that they're even more sensitive to misalignments. You can imagine if you have a very narrow spot that perfectly covers the center point of the star, if it drifts even slightly off to the side, you lose a ton of the ability of the chronograph. So this is just an example of defocusing the chronograph by a small amount. And you can see with a normal pupil, which is on the left, this is a Keck detector. You only lose like an order of magnitude off on the side. So if you look here, this you lose a very small amount. But with a vortex, just that same amount of defocus causes it to lose like 10 times the contrast. So keeping the wavefront aligned is really important. So if we look at the same schematic that we had before, just stolen from a different place in Google, you have the same thing. You have a wavefront coming in. So this is like a Keck or a Subaru or any large modern telescope. They have a dedicated wavefront sensor, and the chronographs use that, of course. They run the best wavefront sensors they can, the best deformable mirrors they can, but there's still this beam splitter here. And after that point where the light split off to the wavefront sensor, there can still be issues. So there can be slight misalignments in the optics. Those can vary over the course of the night. They can vary temperature, they can vary gravity. And there can just be things that the wavefront sensor is blind to that end up sneaking in past that point. So this stuff past the point where the wavefront sensor can see they're called non-common path errors. And that's what we're trying to fix. So I'm going to skip a lot of context here because it's a very deep field and I'm not trying to cover it. But one technique that Michael Bottom's been involved with, which is really cool, is so there's this problem when you have these kind of symmetric issues where you can't decode if you have if a wavefront is sort of even or, even across the pupil. Oh, sorry. If it's even across the pupil, then you can't determine if it's positive or negative, basically. So focus is one of those. If we went back to the original image, you would see that a negative focus, so a focus that's too far this way, looks identical to a focus that's in the opposite direction. And so a single image won't cut it. Unless you do something interesting with optics, unless you do something interesting with something else. But, as a example of how far back this goes, the oldest version I know is a microscope focal plane technique that was in the 40s, I believe. And so what they would do is if they're trying to get their microscopes optics improved, they would scan the microscope through the focus. And that was how they disambiguated modes that were ambiguous. So these techniques go really far back, but most of them involve doing some kind of calibration step like that, where you move some optics or you change a polarization filter or you change something about the optical filter. And that's because you need phase diversity is the buzzword. So the way Fast and the Furious works, though, is it essentially just monitors a sequence of frames, 2 frames at a time. And so if the first frame it looks like it's a bit of defocus, but you can't tell which direction it is. And then there's an actuation that goes in one direction a little bit, and it ends up going in the wrong direction. Now you have the sign of the error. And that's pretty much the entire technique. This looks really complicated, and it is, but it works really well. It's on Keck, it's on Subaru. It works without a chronograph. And so this is fast and furious. Michael Bottom's previous grad student, Sam Walker, extended this to a Leo chronograph, and of course called it Too Fast, Too Furious. So mine got named Tokyo Drift. So it's essentially the same technique. So now instead of just feeding a single image to the neural network, you feed it 2 images and the actuation that happened in between them to disambiguate it. And I'm not going to go super duper into detail, but it makes the model more complex. It makes training more complex. But I figured it out, and it actually works pretty well. I have simulated results. Like I said, I got it actually working on the telescope, and he sort of immediately sent it. He sent it. So I was putting it on the vortex on the Subaru, and I believe he sent it immediately to the person who invented the vortex. So people seem to be pretty excited about it. But I'm, again, not going to spend a bunch of time on it, but it's, I think, an important extension of this technique. The next thing, and I'm very brief here, is reinforcement learning. So everything that I've talked about so far is supervised, where you have a known input and a desired label. So you know what the label is for every input. Reinforcement learning works differently. This is the kind of machine learning that solved Go. It's also the kind of machine learning that makes chatbots better by interacting with humans. So how it differs from supervised learning is that instead of having this direct regression, it's formulated as there's an agent and it's interacting with an environment, and you specify some kind of reward, and it just tries to maximize it. That's all there is to it, except that it's really complicated. But I have converted most of the problems that I've talked about and a couple more into reinforcement learning environments. I'm starting to work on them. Some of them work. Some of them train surprisingly fast. So imagine instead of for every frame giving a model, here's 35 values that you should remember. And from each of those 35, it can propagate data back to the original image. So it can learn all sorts of relations from 35 data points every single interaction. That's why supervised learning is so efficient. But with reinforcement learning, all you're doing is saying, no, you did a little worse that time. No, you did a little better that time. It's literally the entire thing. And what's amazing is that it works really well. And what's great about that is that you can specify goals that you can't directly tell what the answer is. So one of the problems we have with ELF, or one of the things we want to solve, is how to dig deep chronographic holes. And I'm not mentioning that in any detail here, but you know, you can't tell it every frame exactly what the answer is, especially if it's interacting with a complicated system that's evolving in real time. But with reinforcement learning, you just tell it, make that section of the image darker, and it gets better at that over time. It's kind of magical. So I can see a bunch of uses for it. The first one is the supervised models are only as good as the training data set that you gave them. But if you just let the agent interact with the environment over time, it learns a lot more quickly what are realistic, residuals and errors. The next, I think, would be really nice is instead of this step where I take my model and then I give it to, and then I spend weeks trying to figure out how to make it match on actual optics. I instead take a model that's already learned basically all the features that it needs to know. And I just let it interact with the telescope on the bench. Like Skexeo has a amazing bench that I really appreciate the Skexeo team that you can grab during the day, and you can just take tens of thousands of images an hour or something and just crank data through the system when no one's using it with real optics and, you know, broadband laser and all sorts of great stuff. It's the actual instrument that's used on the telescope. So instead of trying to figure out what all the systematic errors are and what all the transformations are and what's the influence function and what's different, you just let it sit on the bench and interact with it, and it learns that. I think that is the right answer because I didn't enjoy doing it. But I also think it's more robust over time. Whatever alignment you did won't necessarily last. And then, yeah. So, and I already covered the dark holes as an example of something that you don't know. Yeah, so future work that I was potentially going to work on if I continued in my PhD, which I'm not, but I would be happy to keep working on, is predictive control. I think is really important. So essentially, you know, we always have this penalty of however long it takes the model to learn. But even if you didn't have any time in the model learning, you have the exposure time. You know, you have the time it takes to send the actuation. You have the, you know, any number of things. So there's always going to be some lag. And if you could just take some images from previous and get the evolution of the atmosphere, you could predict exactly the time you needed to do the actuation. And it's something that's been worked on a lot. And there's like well-known solutions, I think, or, you know, good solutions for frozen in atmospheres, which is a common simplification that seems to be true sometimes. But the actual atmospheres that you're going to get on a lot of nights are going to be very complicated, or they'll sometimes be extremely complicated, involve multiple layers going in different directions, or wind-blown problems with the dome, or any number of things. So if you could just give a model a lot of data where it sees how the atmosphere evolves in reality, I believe that it wouldn't be a problem. And then the other thing is similar, is pre-training on just a ton of data. And so that means you don't have an actual goal in mind when you do this. You just take a bunch of data that exists and you essentially compare it to itself. And from that, you can get representations. And those representations can then train a model. And that's what all of the generative AI stuff is built on. That's what a lot of the large language model stuff is built on. I think it would be useful here too. I have other ideas, but those are two that stuck out. So appreciate it. Thanks for hosting me. And if you have any questions.
Any questions up there?
Okay. And sorry that went so long. I didn't realize. My bad.
So, and one of the problems that I know we worry about is actually running in real time. So once you use whatever techniques you use to create the network, we then have to be able to execute it at a speed that keeps up with, even if it's predictive, something that's probably what, 100, 200 hertz.
Yeah, I'm sort of cheating in these ones. These are like 400. So that's part of why they're doing so well. But okay. Yeah, I've sort of been designing for around 200 hertz.
Well, so I'm wondering if we don't have GPUs, we don't have PLCs that we build specific to the networks that you've trained. Is there a way, do you think, of constraining the architecture of the network to architectures that can be implemented in real time? And so as you create the network, you're also aware of the problem of executing rapidly, and you constrain it in a way that maybe doesn't penalize the efficacy of the network you end up. Have you thought about this issue?
Yeah, I think there's a lot of different ways you could try to tackle that. There's the architecture search, like I've already done a decent amount of. I found a range of models that were huge range in size from, 60 megabytes worth of parameters to 3 gigabytes worth of parameters. And they actually, in that period of time that I trained them, got to similar performance. So I think there's a lot of leeway to go down to a much smaller, more quick network. And there's also techniques that they use in large models called distillation, where you can take a model that's learned very deeply from a data set and distill that into a smaller data set or into a smaller model without retraining on the entire data set. There's quantization. So reducing the accuracy of the numeric computations at each step helps tremendously. And like large language models have gotten down to 2 bytes, 1.5 bytes, I think is the latest claim that I've heard. 1.5 bits, 3 values. Anyways, and they claim that they don't lose any performance when they train in that way. So there's stuff like that. On the hardware side, one thing I don't think that we've really looked into is there's lots of machine learning that happens, as they call in the industry, on the edge. So on the edge is anything like a robot or like a self-driving car. And all of those things have really tight latency requirements and really optimized to go as fast as possible. And I think we're not even scratching the kind of speed that those can do. So I think at some point, when you're closer to needing this on the sky, you just gotta try to buy something like that and just see how fast it can go, or lease it if that's possible. But I don't think they're that bad. A piece of optics costs more, So.
Okay, so what's the fastest machine learning AO system in practice that's now on the sky?
I don't really know the answer to that. I know Skexeo does a lot of really clever stuff, and they have a small cluster of computers. So they have a machine learning dedicated real-time computer, and 6 computers all talk to each other in real time, and they've gotten that fast enough to run AO on and do transformations on top of. And so probably the answer is ask Skexeo or ask anyone related to them.
Thank you, Ian. I was wondering now, have you tried to use transformers? Transformers? In all the experiments you have done so far?
Transformers. Yeah, no, I think that would be potentially pretty useful. So you could especially imagine it in the evolution of the atmosphere. So transformer is what's behind the large language models. And so all it does is it takes a big sequence of inputs, and it learns to pay attention to what's the most important to the output. All it does, it's pretty complex. But what large language models do is they look at that whole context and then they predict one more word into the future. And same problem we have. If you look back to the atmosphere, you want to predict the future. I did mention this to someone at CFAO, and he was skeptical that you would need that much context. And that sort of argument sort of makes sense to me. Like, how much context do you really need? Do you need to go back 20 milliseconds? Do you need to go back 50 milliseconds? Do you need to go back a second? It's like only once you get to really long contexts do transformers become like really valuable. So, but yeah, it's a good idea.
When I have one kind of a silly question. I understood the Strel in an optical situation would be 1. If I understood correctly what Estrel mean. So in these graphs we're seeing now, why the green light isn't always 1?
Yeah, that's a good question. So we can sort of see it. Sorry, I have to go back pretty far. So this, wait, there you go. So you have this atmosphere, and then you remove, all you can remove from each of the sub apertures is just this piston, this tip, and this tilt. So once you remove that, there's still all this higher frequency errors that
The
you
high
can't,
order atmosphere error.
that you can't remove. And so this is a particularly bad case, but in this case that there's
So that leads to my next question. That's how could we remove this high? I mean, it's not doable with this kind of system, right? It would need a
yeah. And so I think the original plan for Self was to also have another AO system, like a Max sender. And that would be more responsible for the higher frequency stuff. But actually, just because I like my own stuff, I have trained this model to also just instead of piston tip tilt, and instead of Zernickeys or any other thing, just find the best correction for a DM. So if you have a DM with a certain resolution, what piston or what poke do you put to each DM element to fix the atmosphere? And that surprisingly worked well. I didn't think that would work. So I think you could also get the higher frequency information from this, but we haven't tried to train it yet.
Thank you.
Yeah. Thank you.